Over to you, Prof.
Thank you. Thank you very much, Janaki. I appreciate that. Hello, everybody. Is this clear? Should I start? Okay, I'll kind of switch between the two sides, go a little bit here and a little bit there. So I do know that I have a lot of slides here. I will positively end at 5 o'clock. Okay, we will skip as needed the slides. I'm also assuming this is a fairly diverse crowd, but if we need to go more technical, I can go. Okay, we will see. So this work is essentially an operation research style work, as opposed to a, and many of us work on these topics. So, I'm thankful to Professor Shanti Kumar, who essentially told the main result that I will show you was derived by him. And this is a paper. Most of what I'll be presenting is a paper that appeared in Informed Journal of Data Science. There is also some other work that I did afterwards with Preet, and that is also described here. Okay, I have to say this, although I don't know why Amazon does this, and I'm saying this in a YouTube link. They make me write Amazon, but they also ask me to do this, which is to say this has nothing to do with Amazon. So I want to make that very, very clear. Okay. All right. This is my attempt at using ChatGPT. This only this. Okay. But ignore that a little bit. But my ChatGPT. So this is what is happening. You're sitting at home, okay, and you need to go to a restaurant. And this actually happened in real life. Okay? There's a restaurant called Possibilities in my hometown called Syracuse, which is about half an hour from my house. Okay, and I don't need to speak this loudly. Possibilities does not take reservations. Possibility does not take. But what it does is it puts you on a list, on a waiting list called Waitlist Me. Basically, what that is it puts you in a virtual queue. Okay. Then you keep checking your phone, and it gives you all. I'll show you a picture of what it gives you. And so I live 30 minutes away, and I need to show up when my turn occurs, right? So maybe I'll show you the next slide. So I'm right now, let's say 50th in the queue. I won't get my turn for another 45 minutes. So I can leave after 15 minutes, go, and I can go in there, okay? So the question is, when should I leave my house? Arriving early or late is a problem. I mean, you don't want to arrive early because you just have to sit there doing nothing. And arriving late is a problem because you might not get a nice seat. This is very common. I wanted to give an example that a lot of people can relate to, but I will give you a ton of other examples where it can be used. All right. This is from my iPhone, which you just saw. This is me, G. That is me, and I am 20 minutes. I've already waited in this queue. This is exactly from the phone. Okay, so this is the Waitlist Me app. The person has been waiting for 52 minutes. Is somebody with the letter A. It only gives these three pieces of information: what is the name of the party, which is whatever your first name is, and the group size, and how much time you waited. Okay. Yeah, so that's a very good question. So is this first come? It is first come, first served because they make this public. So you don't want to disappoint somebody by, if this guy goes before me, I'd be very unhappy. So yes, but because of that, they do first come, first served. Okay, but we are all waiting.
Because they went on practice before the restaurant opened, or yes, that's the
I think that's a good. So this restaurant is super popular. So a lot of people go. So you have to put your name down. If you don't put your name down and show up there, it's the same problem. Then you have to wait for 50 minutes in the restaurant. So now I do want to say one other thing is that many restaurants, I know for sure in the US, but I'm certain in India also this is happening, that that instead of making scheduling, let us say you have times like 6 o'clock, 6:30, 7 o'clock, 7:30, times like that. The downside there is the service time, the times that you are in the restaurant can be very varying. So what happens is you will end up wasting a lot of your resources. Okay. Cool. Thanks. So this is an alternative to actually scheduling somebody, saying you have a 6:30 appointment, you have a 7 o'clock appointment, because that actually wastes a tremendous amount of resources. So you might as well say this, and then you show up and you go in. So they never waste any. Yes, sir. Yeah. Correct. So that's a very, very valid point, and I am going to say that is something that correct. So for example, if I am number 20 and I say there's 52 people waiting, 52 minutes of wait, so much more time of waiting, I might as well ditch and leave the system. I am going to assume that this doesn't happen a whole lot. Now I will tell you how one handles that. There is like a deposit that you pay, so that you're surely going to show up there. Okay, so you do pay a deposit, and if you show up, then that deposit get removed from your bill, final bill. So that way, this is one of the problems. So I do want to say this too. So restaurants have a very small profit margin. So they have everybody they want to serve as many people as possible. So they want to make them come. They also don't want to waste spaces in the restaurant by not having anybody in there. So both the arrivals are important, as well as entry is important. So they kind of do those things. So that's a very, very valid question. Let me give you a few other examples, just because I don't want you guys to think that this is only a problem in restaurants. It's in other places too. And I think the most promising example of this is in the urgent care. So imagine, if you are sick and you have to, and urgent care is essentially the same as a small clinic where you have, you put your name on a virtual queue and then you go in when your turn comes. You don't want to go in too early because there may be other people are sick and you don't want to get the sickness. So that is the cost of going early. You don't want to go late because then you go back to the waiting list and then whenever your turn comes, you come. So you have to kind of show up on time, and you have to drive. So you have to go or drive or take the bus or something like that. It takes you time to go from your home to the urgent care. So same situation, okay, same problem, but a different context. Same with the car wash. I mean, this is a classic US thing where everybody goes to car wash. I don't know why. They go, and so you don't want, there is no space as well for a bunch of cars to wait to get car wash. So you might as well dial up and then show up when your turn comes. Same with the haircutting salon. So in a haircutting place as well, the same situation. Since it takes different amount of time to serve each person, for get a haircut, you want to be sure that somebody is being served all the time. You don't want someone to say, okay, it is 7 o'clock appointment, 7:30 appointment, so the guy gets done in 15 minutes, then you have 15 minutes of doing nothing. Okay, so that is not a good use. So the same problem is being solved here. Let me give you a few more examples. So in an amusement park, this is again popular, this is already there in most of the amusement parks. You go in and then you say, you don't have to stand in the serpentine line. You say, I will show up at 11:15 and you get a turn. Now, this is not the best example because the time each person takes is somewhat constant. It's not terribly stochastic. So it's not of tremendous interest. This happened again to me in real life. So so we are going from Raleigh to Newark. Okay, Raleigh is about 1 hour and 15 minutes from Newark. Syracuse to Newark is also 1 hour 15 minutes. What the plane tells, this is actually true. The guy there says, Newark, you cannot land. And don't leave and just circle around Newark Airport on the sky, because that uses up a lot of gas. Okay, so what they say is, you just sit there. Okay, you take off when I ask you to take off. So that is basically so many times. I mean, this is not the exact situation we're modeling, but here too, you put yourself in the queue, and then the air traffic control has everybody's names, and then they say, okay, now you leave. Okay, so you have an idea of when your turn comes. Then you have to go take off and then go and land so that it's the right amount of time for you. So those, and the food delivery service again with your Swiggy and other Zomato and all those companies as well have the same problem. You don't want a guy to come stand in your restaurant waiting for the food to come. You want the guy to show up just when the food gets ready. Okay, so there are multiple such examples. So here is the modeling that some of you guys are interested in. So this is where, now I do want to say this, and this is not so important for the ECE type of crowd, but I show this to students in the business school, they're thinking I'm solving the problem for the restaurant. So let's think of a restaurant example that's just easy for all of us. I'm not solving the problem for the restaurant at all. Okay, I'm only solving it for the user, for the person who comes there, who wants to enter the restaurant. So you enter the restaurant here, and let us say you are number n plus little n plus big N. Okay, that is your number. Okay, so in my case, after a while, I was 20th, but I would have started, I think I was 40th or something like that. So then the first person comes, second person comes, and so on. When you wait and you record everything that happens, you don't have to do it. You can have your app actually record that. And it will tell you how long it took you to go from one, or rather, how long it took each person to come down by one. Then you have a bunch of data here. This is the exploration phase. Then you exploit after this, where you're trying to decide at this time, okay, when should I come? I'm saying return to the system. It's really not anybody leaving or returning. Ignore those words. So right now you are here and you're trying to decide when should I show up here. That includes some travel time. Okay, there's some travel time. And you decide when to leave so that you come. In this case, you're arriving before the event time, so you are incurring what is called a holding cost, which I will talk about very soon. Sometimes you could come late. That could also happen. Now, so these events correspond to the change in your position. So in this picture, every time you go from number 20 to number 9, oh no, not number 20, whatever number I am, when I go up by one, every time I go up by one, that time gets moved. I will have some notation, but it's not crucial for you to memorize any of this. So this is the random quantity, okay, when the event is going to occur. And your decision is when to come back to the system. And there's a holding cost H, which is incurred here because you come early.
Just you stop exploring it. At that point, you go to the restaurant.
No. Actually, the exploring time, and we will see in another example, the exploring time is fixed, or rather, the n is a fixed number.
You can decide to leave not at n plus 1. You can decide to leave at
Sometime here you can leave. Yeah, you can leave any time from now, but you decide here. You don't wait. I will make that model simpler later.
I'm saying while you're stopped, but you're simply getting more information.
Yes, and I do have that version also. Okay, so for this version, the simpler version, you stop here, and then basically, you don't want to just go on. So this is where you're having your phone to decide. And this exactly happened. Actually, my son and I, when we went to the restaurant, this is exactly what we did. We calculated. We said, okay, we need to leave now. I will say we still had 10 minutes to go, but that is a different issue. Okay, so but. Yeah, so you have to decide when to leave after doing some exploration. Otherwise, you have no idea what is the time between those events. Okay, so you get some data. All right. Then the other thing is the penalty cost. Now, this is purely artificial. So, so this penalty cost is if you don't show up on time, what is the, so somehow, let us say we can give a cost to it. Later, I will make that more realistic in another example. Okay. So this is called a data-driven online optimization problem. Why? Because this is the data that is driving it. You're getting events one after the other. And this is an online optimization problem because you are trying to decide here by looking at the states online, you're live, and you're trying to make a decision. So what should this arrival time U be so that the expected cost is minimized? Okay. Notice that we do not observe the system, and that is exactly what Parimal was asking. We do not observe the system after this time. Okay, that is an assumption that is made for now. Yes. Correct, and you keep going down by one. You keep going down by one, and at this point you will be number 0. I mean, this is when you have to enter. Yes, exactly. And little n is the time, is the amount of this is when you explore, and the big N is when you decide to go. Yes. Thank you. Any other question? Hey, do you need to give a mic or you're okay? It's okay, right? I'll try to repeat the question for those who are online. Both ends are fixed. Little n is fixed, big N is also fixed.
So why is it online optimization? Is it because you can make a decision at n+1, n+2, or at any time, or why is becoming online optimization?
No, that's a good question. Yes. So, no, in this case, you make a decision at n only, okay? In this case, you make a decision at this point as to when you're going to leave. So the U time is some time that you wait at your home itself, then you drive and go. So, so that is the entire time is what you decide at, because you're saying, okay, I'm not going to look anymore at my clock. I will later make the, which is exactly your question. I will later make sure that the n plus first, n plus second, all those are also, I will re-evaluate when I have to leave. Okay, we will do that as an extension towards the end. Very good. Okay, thank you. So this system is a virtual queue where you are the n plus nth at time 0. Okay, and these events correspond to, we've seen this. Now, the next assumption that we make is that the time between these events, so 0 to event 1, event 1 to event 2, each of these times is according to a gamma distribution with unknown parameters k and theta. We don't know these parameters, but it is there. Okay. Now, it's a very reasonable question to ask, why gamma distribution? Why not something else? Okay, and the answer to that question is that we want to pick a distribution which has two parameters that we could estimate, which also is such that it is not, it takes positive values. I could have picked normal, but normal has a problem. It can take negative values, so we don't want that. The other thing is, whatever mean and whatever standard deviation, this will still work. So therefore, this is a decent distribution to pick. I promise you, I will show you an example where the actual data is not according to gamma. It still works, and that is the point that we were discussing earlier with Parimal. That these assumptions are not crucial. Okay? We just made it for mathematical reasons, but not for. It is not crucial that they have to hold. Okay, so this I think we said we explore for the first n events, and then we say the what you exploit is to return at time u. All right. So, yeah, I think most of this we have said, but I'll quickly go through. So, x is a random variable that denotes the time between n and n plus first. Decision is this. We saw this. Yeah. Okay. So, one more example. This is a slightly different one. So, let us say you have placed an order for making some items. I told it to give me examples of 3D printed items, but it did what it did. This is ChatGPT. So anyway, so let's say you have a bunch of 3D prints that you want to make, and you send it to a company, and then they say, how long does it take to make? Well, you first observe the first n of them, and then you say, okay, you will guess maybe the rest will also take the same amount of time, and then you say, okay, you come back at say 10:45 a.m. to pick it up. So again, as a customer service situation, you don't want to be guy to come and then you have to wait for too long, as well as not wait, as well as come late and then you have to carry inventory. So it's the same problem that is there in many systems. This is the example that we will see, okay, for real data. So this example, maybe I will wait later and show you, but this example, what is happening is there is this, in Los Angeles, there is this bicycle rental, where you go, you rent a bicycle, and they are kept in these racks. Okay, these racks are there, and you take the bicycle and you go, and you can leave it anywhere you want to. And so, if every person, there are n plus n, little n, this should have been one, should have been little n plus big N number of people are coming in. I'm sorry, those are number of spots here. So you observe how long it takes for each person to come, take their bikes and go, and then somebody has to come and replenish those bikes, okay? And when should you call him? Okay, I will explain this problem one more time when we look at the actual data. Same thing for fashion items and so on. So I'm just making a case that it can be used in, this relates to what I was telling you earlier today. This application is very wide, okay? It can solved in many situations. So let's say there's a new fashion accessories, and then you look at the first n items to see how long it takes, how many people buy it, what is the rate at which people come in and buy, and then you say, okay, please give me one more replenishment of this item. So for the same reason, you don't want them to arrive too early or too late, because too early means you have to store them somewhere. Too late means you will lose out on opportunities to sell them. Okay, so one last time for you guys to see this is, so we have these events, gamma distribution. So think of this x, therefore, each of these events is gamma with parameter k and theta. We don't know the k and theta, but whatever it is, this x itself is the sum of n number of them. So because the sum of n of them, that is also going to gamma distribution. Another reason for picking gamma, because sum of gammas is also gamma. So that is nice. So, but with a different parameter, n times k, where n is known, but k is not known. And this is why we don't want anybody to leave in the middle, because then that will mess up our n, which are extensions that we will talk about. So the mean of this is n times k times theta, and the variance is n times k times theta squared. And there's a holding cost and penalty cost. So this is our problem statement. And so what we're trying to do, we're trying to minimize the expected cost. Now I am doing this problem for an oracle. An oracle is one who knows nothing but k and theta. There's only two things they know. Okay, they don't know what is going to happen and so on. They know k, they know theta. So this oracle, if you give this problem to it, what will it do? This, if you are familiar with the news vendor problem, is the standard news vendor problem. This has been solved by many people. So what happens is you're trying to ask the question, this is the distribution. This is the CDF of x when there are n times k is the shape parameter and the scale parameter is theta. So then you can solve this problem. Well, all this is saying is if I come early, then I have to wait u minus x. X is the time that you show up. U minus x is how much you have to wait. You have to pay a cost of p. And this is the PDF, which is the derivative of the CDF at that value. Plus, if you come late, then you pay h. Oh, sorry. If you come early, you pay h. Sorry. If you come late, you pay p. I messed it up. Anyway, then you solve this problem. This is a standard news vendor problem, easy to solve. If you take the derivative with respect to u, you will get the optimal value, which is given by this. Okay? Nice things will cancel all over the place. And f of u star will be h divided by h plus p. So this is when you should come. So essentially what this is saying is if the holding cost and the penalty costs are equal, then you will arrive exactly at the median, okay, at the median of this distribution. That's what it says. We make another approximation for a reason that I'm about to say. When n is large, we can use central limit theorem and say x is approximately normal with this mean and this variance. The reason we do that is because normal distribution, if I use this and get my u star, then my u star will be independent of everything like n and, no, not u star, sorry, this h over h plus p. If you want to, this alpha, which is basically the inverse of this, is only dependent on h or h plus p. It is not dependent on n, k, or theta. Okay, so that is what makes it very convenient. All right. Now we are switching to the real model, which is when the theta is unknown. How much time? Okay, I will go a bit faster. So when theta is unknown, what do you do? And this is why I thank Professor Shanti Kumar, because he has a bunch of papers on this topic called operational data analytics, which is very nice because it tells you what to do when theta is unknown. Okay, so now, for now, and in a few slides, we will make k also unknown. But first, we're going to make theta alone as unknown. Okay, only theta. There's some magical reason where only theta is unknown, but k is known. It is also useful to do that when you have exponential. Exponential k equals 1. That is for sure. So, so for that reason as well, we say we know k somehow. Now, then what we do is we collect n samples of these realizations, d1 up to dn, which we denote as little d1 to dn. These are the times when these first n events occur. Then theta hat is just this because the mean of the gamma distribution is k times theta, in this case theta hat, will just be equal to, so this is how you would estimate whether you use method of moments or maximum likelihood estimator. This is the value of theta, whatever method you use. Okay. So this this value of theta hat really depends on what observations you got. Okay. Now note that n is small. Okay, so that is also important. When n becomes really large, then this theta hat will become equal to theta. There is no two things about it. Okay, because of law of large numbers. Okay? So, but we assume that we don't assume. There's no point in looking at it forever. Okay, so this is small. I think so. Yeah, I think the main thing here is depending on how these realizations happen, you could get very different values of theta hat. That is the main point here. Okay. Let me see. Okay. Now I think this is the point, and I will stop for questions. Okay. So one method to solve this problem, which is often done in engineering, is this method called predict and then optimize. So that means in the first stage, you predict this theta. Exactly like how we did this. Theta hat is essentially theta. You predict. Okay. So you predict this theta as this, and then you, okay. And then you try to use that in the optimal solution. So what you do is you take this theta hat, which we predicted like before, and then you say, okay, I will arrive at this time. Okay. Now, if the realized value of x is x, then this will be the cost. Okay. So, so notice the difference between the optimal value and this value. When theta is known, then this will, instead of theta hat, you have theta. Okay. And this will be the total cost. And what we are trying to see is, would these two numbers be similar or would they be different? Okay, so that is what we're trying to say. And with these u stars are different, it will be different, right? Because theta hat is never exactly equal to theta unless n is supremely large. Okay, so the question is how bad they are. And this is not a mystery novel. I will tell you, this is a terrible idea. Okay, you will see that there's a huge difference in the values. So the traditional approach of predicting what theta hat is, or rather predicting what theta is as theta hat, is not a good idea. Okay, that is the essential story. Then this operational data analytics, I think since I want to quickly go over this, what we show is that if I have a z so that I multiply, I'm speaking like I'm talking in the US. If I have a z, so I multiply z by theta hat, then this guy becomes a better estimate. Okay, although remember that this theta hat is the unbiased estimator. Okay, that is the best estimate you can get. But the problem is not to get an optimal value of theta hat. Okay, the problem is to solve the actual problem. And in which case, I'm saying instead of theta hat, I multiply it by a z. Okay, so that will be better. It's a very simple scaling. Okay? And it works only if a condition is satisfied. I think I'll say later why that is the case. Now, therefore, if I multiplied this theta hat by z, I get z times this value. So this is the same as this, except I multiply by z. Now, this z has to have three properties. First property is I can choose a z star, which is the optimal value of z, which will produce the lowest cost. Secondly, this guy should be independent of theta, and that is why this condition is this. I guess this condition. This guy here. This condition is there only because only that will ensure that it is independent. Okay, so I will quickly go over this. So essentially, the way to prove that, and I don't think I should go too much about how to prove this, but I'll quickly tell you that you can write this uppercase theta hat as a random variable, which is the sum of the d's, which are random quantities that you get for the time between events, and you compute its expected value and write that as eta of z. Okay, I will go over this detail at some point. I'm guessing because of time, I probably shouldn't do. I'm only at halfway, but in terms of slides. But I will go over that. If you have any questions, I will go over that. So now what I'm saying here is that this value, maybe I should stop and ask you the question, because I think I'm going too much to these slides. Yes. Let me see if there are any questions, and then I will tell you how to solve. Are there any questions?
I don't understand the reason why you cannot estimate and then use theta hat in place of theta. Is it because uh, when you multiply with z times theta, you're getting biased estimate? Is it leading to better MSC or lower MSC, thereby giving you better value of the better optimization than the just taking the unbiased estimate? Or what is the reason for
Correct.
not estimating directly?
Sure. So let me say that. Yeah. So there are two parts of this problem. Okay. So the first part is, do I get a good value of theta hat? If all I'm doing is to get the theta hat, then you should take that estimate. But our objective is not theta hat. Our objective is to get the best value of u. Okay. And these functions are non-linear. So what happens is it penalizes quite heavily if you are having bigger numbers. So you kind of take smaller values. So z will end up being less than 1 most of the time. Sometimes it's bigger than 1. Most of the time it's less than 1. Actually, let me show you the results, and then I'm going to come back and then I'll show you the math, because I know I'm realizing that a lot of these I will show you later. But let me show you, I'll show you these later. Let me show you what happens if we performed an experiment. I think it's better, and then I'll go back and show you that. So let us say we performed, this is pure simulation. I'll do real data later. Okay, so pure simulation, I get n is 50. So 50, your number 57, 50 plus 7, number 57 when you come in. So let's say the holding cost is 10, the penalty cost is 10, holding cost is 6. K I'm fixing as 1.67 and theta is 6. Okay, I'm not doing anything other than that. Now, if I have all these parameters, I generate 5,000 experiments and I create a bunch of realizations. Now, what will happen is that theta star is 6.01, which is very close to theta, because the average of the 5,000 experiments better be equal to this theta hat. Okay, it better be, because this is the average among all the theta hats that I have seen. Then the z star is this. We'll come to this later. Okay. Now, notice the u star on average. This is done by the oracle. Okay, it is 483.53. This is done by the predict and then optimize. It is very, very close. Okay, that is because the theta hat itself, on average, if you take a large number of values, this is fine. Okay, now notice how small the uz is. Okay, it is much smaller than this. That is because z is less than 1. So your uz, so you will leave much earlier than you would have done in these situations. Okay. Now what is happening is, notice now I also used the Bayesian approach. Okay, so that's what this is. Let's ignore that for now. Now what happens is, this is the optimal value. This is the optimal cost, the optimal average cost. Notice how much larger the predict then optimizes versus using the z star. Z star is much smaller. Okay, z star, if you compare with this, is kind of closer, but it's not that close. Okay, this is the best that you can get with the data that you got. Now, I would have to explain the Bayesian one, not the method, but in the Bayesian one, you have to, the prior information is that it is close enough to 6. If you tell it is between 5.5 and 6.5, then it will do this well. Okay, if you don't tell it anything is one thing. If you tell it, if you're giving some prior, you're giving it information that it is really close. I don't think it's even 5.5 to 6.5. It's even smaller than that. You can give it information, then it does quite well. Okay, then Bayesian methods will do very well. Okay, but that prior, giving that prior has become very hard. So what I'm saying here is that if you have a lot of data points, then it is one thing. But here we only have 7 data points every time. And every time after 7 data points, it make a decision. That is repeated 5,000 times to give these numbers. Okay. So you are able to get the theta hat reasonably well on average. But every single value is going to be off a little bit. And what this z is doing is it is asking, saying, if I get too large values, it's a big problem. So I multiplied by like roughly 0.9, okay, bit smaller. So that is what is happening here. I can go over this other part little bit slowly, okay? I just want to say one other quick thing. I'm not going to show you the derivation, but I can if somebody wants me to show. The point that I wish to make is that now if you had exponential distribution, which is what we like when we have to show some results numerically, then you have this structure. This is z is on the x-axis and eta of z is on the y-axis, and it says that there is an optimal value somewhere here. Okay, that is one of the requirements we had. The other thing is that as n becomes larger and larger, I know you can't see these numbers, but it's going closer and closer. This is 1. Okay, I don't know if that's 1, but it is going closer and closer to 1 as n becomes larger. As the number of data points become larger, you're going to average it out quite nicely. But when it is small, it is quite tiny, and that is the essential story that this is doing. Now, when k and theta are unknown, then what you do is you are saying, okay, now we have two guys are unknown, but the story is that it's actually very simple. We just say, okay, we will estimate k and theta and then use the same results we've had before. That's essentially what we do. We have two metrics, the mean and the variance of this d, which is all we have. Which is what we can compute using our n samples. So the mean is given by this, the variance is given by this. And there are two methods. The first method is method of moments, which essentially computes this. But you can also use the maximum likelihood estimator, which makes it a little bit different. Those are the two methods, which you're all very familiar and hoping. This is a set of pictures. Okay, now this is just simulated with theta equals 6 as the value, and n is 6, not 7 like we saw in the example, 6. So then what happens is when k is known, this is the distribution of the values of theta. Okay, so what happens is theta hat can go take a large number of values. So this is the distribution of theta hat. This is the distribution of theta when k and theta are unknown. So it kind of goes like this. So the values are, so what you get as theta hat can vary tremendously. And here you notice a little bit better, but even here you do notice sometimes it can take very large values. So therefore, it kind of softens it down by taking a z, which is generally smaller than 1. But there's no reason it has to be smaller than 1. Okay, there are some examples where you show it as 1.03 and so on. Okay, so now k on the other hand has only two cases, because either k is known, there's only one line. When k is unknown, it also kind of goes like this. So the point that I'm trying to make is when you do a lot of modeling, you assume that this is a kind of a gamma distribution with this k and this theta. But actually, if you take data, it is not easy to get these values exactly. And you want to see what happens. This is the slide I showed earlier. Now, what if the k is also unknown? Same example, okay, same n, same HP, and so on. Then you run this, and there are a few more things to notice, but the point here is the theta hat is now different. So notice that it's only 5.5 using method of moments, it's 5.2 while using maximum likelihood estimator. This is with 5,000 experiments. Okay, so this is the value, but notice that my k is also very small. Okay, so it is a little bit better than exponential. That's all. Yes, sir.
For example, if you flip from h equal to 10 to
you
h
reverse
equal
those
to
numbers,
6,
10 and 6.
Z should be greater than 1.
That's a very, very good question. So I also thought like that first time, but it is not so. It is more to do with how, because on one side only you kind of can go off to the infinite. It is not. If you switched also, you get the same result. Okay, but that's a very good point. Okay, thank you. So in fact, I will show you. I think I have another example where I'll show you that to you. So look at k also. So here k, notice that k is also very high, higher than what it actually is. And that is my point also to say that, so generally whenever you collect data, it is underestimating theta but overestimating k in some sense. I don't know why that is happening, but anyway, this z star, whether you use method of moments or maximum likelihood estimator, is all 0.9. Then notice again that whether you use, this is 485.9, right? It is the same data as this guy. So which is 483 here. So this 483 is the optimal. So I didn't put that solution down. So that solution is exactly the same. Whereas with the z, it is a little bit, you go a little bit earlier. You essentially arrive a little bit earlier than when you would arrive here as a person who's going to a restaurant. But if you see the cost, this is the z, theta is the cost. The average cost is significantly better when you have the z. But it's not there's no major difference between method of moments and maximum likelihood estimator. These are, it just happens to be like this. It could go the other way around also. But if you use some other methods like sample average approximation and Bayes method, it actually is much worse. So this is therefore a very good method. And this is the predict and then optimize. So this is how we saw. But all this is simulated data. Now you can ask, well, show me some real data. That is this. Okay. So when you get real data, and this is the same example that we had before. So an automated bicycle rental stand. This is in Los Angeles, where there are n plus n docks. Okay. Now I will, I don't have numbers for them because every day the numbers vary. Not exactly the docks, but the way I solve the problem. What we say is the stand opens at 12 p.m. Okay, so 12 in the afternoon, and then the customers arrive one by one. There's a guy. So the way they do this is they will swipe a credit card, and then they will take the bike, and then keep going, and they return wherever they return. Okay, so what we do is I will take as many customers that arrive before 1 p.m. and just observe the times. So this time I'm doing something different. I am not making n as constant. I will say whatever value every day, however many come before 1 o'clock, that is what I observe. At 1 o'clock, I need to tell somebody, hey, come and deliver a bunch of bikes at say 10 tonight. Okay, because it takes some time for them to collect all the bikes, come and then drop off and all that. Okay, so so by 1 p.m. you need to decide when to return with these n plus n bikes. Again, the same situation. If you come too early, if this vehicle comes too early, and let us say there are 1 or 2 or 3 bikes still left in the stand, the guy has to wait. Somebody has to wait. Okay, because you have already asked for n plus n new bikes, so they'll have to wait till they get enough of those stands. If they come late, then you may have some customer who's coming in, they don't have a bike. Okay, and these are actually kept near train stations, like your sandal soap factory station. Okay, there's a bike standing there. People just ride that and then they go home. They can come here, for example. Okay, so like that, they have these bikes that are there. And so you don't want anybody to show up very late and then they don't have a bike. So that is the other cost. So this is real data from this site, from Metro Bike Sharing in Los Angeles. And that result is interesting in that I took 90 days of data, 90. And between January 1st and March 31st, I guess I have a lot more data than that now. So there are 16 days we had fewer than n equals 4. And I dropped that because if you had 3, 2, or 1 bikes, then getting even the mean and the standard deviation almost makes no sense. I could have used it, but I think whenever it is 2, less than 2, I cannot even get a standard deviation. So I didn't want to pick numbers that are very small. I needed at least 4. And so all those days, I compute D1 through Dn and find when it is good and so on. So this is roughly what the K star looks like, and this is roughly what the theta hat looks like. Doesn't mean much, but I show you the results. And this is how the method of moments versus the z, how the z's change. Z's have, so notice that Now that you have real data, it doesn't look anything pretty like the previous pictures. Okay, it doesn't look anything like that we've seen, but you kind of see a structure like this and kind of see things going down. Now, these are the values that are more important. Now, if you see theta hat, this is what I only took method of moments. I don't think I took the other one, and because it worked really well. So this is my Z star. Now, notice the following. This is most important. The inter-event times are not necessarily either according to a gamma distribution, nor even identically distributed. We just took that beta and just ran with this problem. Okay, so that is the important part, and I think that is the part that I really want to tell you guys. Two things. Thing one is, if you estimate it and then use it for optimization, it is not very good. The second thing is, it doesn't matter what distributions actually go into that. Does not have to be an identical. It does quite well in comparison to the other method. So now notice we don't have any oracle. I don't know what is the best time to come. Okay, if I had full data, that's another issue. You would exactly show up. Okay, but that is not what we're observing. We have an oracle who just doesn't know the k and theta. So we don't have that. So what we do is we see what the theta, k, and so on. So notice here the z now here is only 0.85. It's even smaller than what we've seen before. And this is the average value of x bar. This is the average value of the time that it takes to actually become empty, the stand. And the predict and optimize picks 388 as the time when you time between when you make the phone call and when it arrives. And this is U star. Notice this again smaller, like it always is. And this is the sample average approximation. This does reasonably well. And this is the Bayes method. And if you notice here, this is the best value. This is a UZ star. This is the best value. And if you compare it against the predict and then optimize, it is a lot higher. And we don't have an oracle to say, what you could have done really, really well. So okay. So now I know that I have some more slides, but I want to see if there are any questions. So I just want to quickly say, there is an impact on stochastic modeling where we assume that there are distributions. So we want to be a little bit careful. So if all you're doing is you're estimating, there are easy methods. But what I'm saying here is, if you're later using it for optimization, you want to be a little bit careful. So predicting and then optimizing is not as effective. I do want to say there's a lot of work in machine learning as well, where you are, let us say you have a machine learning problem where you're deciding some parameters and using it later in an optimization framework. It is better to actually scale those parameters a little bit. Okay, I have not myself done any research on that, but I believe there are other people who have, and they've kind of shown that that way of solving the problem is not very good. I think most of these we are familiar. Okay, let me see if there are any questions, because I know this watch is about 2-3 minutes fast. So I have some more results to show, but let me see if there are any questions. Yes, ma'am.
Can we find upper bound on U star PTO minus U star and add that to the correction to get some good values of U star?
It's a very good question. Can we get upper bound? So I think I don't think so, because the upper bounds technically will go out to infinite, right? Because this is an unbounded distribution. But having said that, in the real data, my guess is it is hard. Am I answering that? My guess is it is hard in the real data to get an upper bound, unless you're talking of something different than that. Oh, empirical data, what is the upper bound? Okay. That we can get. Yes. So what happens, what you're saying is, actually that picture is better. So what you are saying is that we look at the first little n, don't look at the first little n, and use that to get an upper bound, right? that is roughly what the sample average approximation does. So this it doesn't do that. It actually creates a distribution from what is there and gets this value. So it's not an upper bound technically, it's actual value, but it just samples from the first. So there are a little end, right? Then it just samples from there, and that is what sample average approximation is. It is bootstrapping from that value. Okay. But can I get an upper bound? Let me think about it and get back to you. But your only hope is the first little n values. So my point is to say, those n values are themselves, fair. Taking those, you want more values than what you have. That's what I'm trying to say. Other question? Yes.
So just to understand your algorithm, so instead of predicting theta hat, you are scaling it with some z,
Yes.
and then finding the optimal values of z. And that is giving you the new scaled estimate. And then you're using that scaled estimate to as your absolute prediction, and then you are computing the optimal decision.
Exactly.
Okay. So, I mean, there's a general saying or a framework that you should not estimate the parameter just for the sake of estimation.
Correct.
There is a final cost, or the parameters are used for some purpose.
Yes.
And that is what we should take into account for optimizing, just as compared to pure estimation.
Yes.
So is that in line with what you are doing here, or?
That is exactly what was being done. Now, the place where it becomes useful is when you have a small sample. When you have a large sample, your estimate is very good. There is no doubt about it. Okay, so that is where you guys are all probably working on some type of estimation, something like that. But that is all fine if you had a large amount of sample. And that's, if you had only small number, 7, 8, 6, and so on, then it becomes a problem.
Okay. And the scaling is only done for theta or also for k?
Only for theta, yes, only for theta. So k is just taken as whatever approximate value you get using maximum likelihood estimator.
So any particular reason why scaling works only for theta, not for k?
Yes. So that, if you remember the condition, so what happens is, whatever value of z you have, z star will be dependent on k. It will not be independent of k. Because only this scale parameter, that's what's called the scale parameter, is actually, it will be invariant of whatever value you have for that theta value. Because this distribution is that is, whatever theta you get, you divide it by theta. If you see the distribution, you will get an equivalent distribution, and that is why it is. So for with k, it will end up being dependent on k, and that is why those figures also, they're kind of dependent. Good. Thank you. Okay, let me quickly wrap up by going over. Now, we make a few quick adjustments, which is kind of talking about what questions you all had at the beginning. So instead of having it's not realistic to have a cost which varies over time if you come late. So where we're saying you give a lump sum cost C, this is like saying, you have to pay some 100 rupees, 100 rupees too small, 1,000 rupees to go to a restaurant, this is a fancy restaurant. And then you say, okay, this is in with us. If you don't show up, that money is for us. So then it will also encourage people to not put their names in multiple places. Right? That is the problem. So you want people to, like I said, this thing is very small, the profits and so on, compared to most of other systems. So that is that. So then what do you do? And you're also allowed to keep on observing. And this is kind of what you had asked earlier. Here you're allowed to observe as many times as you want and decide to go. So I don't want to go too much of the detail, but then the optimal, if you are an oracle, then this is the time to stop where this is the PDF and this is the CDF, and it is given by H divided by C, and that is a value if you're an oracle. Now it makes it even more complicated because now it becomes difficult to solve this problem. Hence we use a Markov decision process, because this condition, which we had originally been used, the data analytics method, will not be applicable anymore, because here what will happen is this condition will not be satisfied. So we say, okay, we take a reinforcement learning approach, and it kind of uses this method as well. So that's why we put in the same talk. And you can see that the reinforcement learning does slightly better than predict and then optimize. It's slightly better. But notice this oracle. So now the oracle the green one is oracle. These two are the green here and green here is for fixed n equals 3, n equals 5. So when you vary that, it does much better. And likewise, even for predict and then optimize, if you keep n as fixed, it doesn't do very well, because as you get more and more data, you might as well use that. So notice that your reinforcement does a little bit better than that, although it doesn't appear to be a lot. But if you look at it, if you remember earlier, you really have to see the comparison of this number, and this number. So it is quite reasonable, I would say. Okay. And then that same thing was done with the bike share, which is the right side. And you can see that the predict and then optimize, if you are allowed to do this over and over again, I don't know if that is realistic in the bike share, though, because many times you have to tell the guy when to show up. So I don't know if it's realistic, but you could do that for this data as well. And this one is interesting, because I just want to say that if you just picked any distribution, does not have to be beta, and actually every one of the experiments we had a different distribution. And when my student and I did this, I created the data that he needs to use, and I never gave him anything of what distribution it was. In fact, I also didn't know. It was randomly generated distribution and so on. And so the data was completely arbitrary, and it still did quite well. Okay, although I agree that it's not a big difference between predict and then optimize, and that is something to be thought about. I think that's about it. I have one more slide, but now, okay. I think since we are running out of time, I'll say that in future, I would like one big assumption is that the time t has been assumed to be a deterministic value, the travel time. Okay, if you're sitting in Bangalore, that doesn't make any sense. So that has to be changed. And hopefully this paper will get accepted, and I'll present here in Bangalore on solving finite state Markov decision processes where this P matrices, are also not known. Okay, so you have Markov chain where the P matrices are not known. You're estimating as you go and taking actions. Okay, so then what do you do? Then there is this whole issue of, this is I think something that we also discussed today, which is Parimal and I, where we were saying if you use a physics-based model to solve these machine learning problems, then that is actually pretty nice, because it is doing the opposite, reverse of what we're doing here. There we are assuming the physics-based model works, and then you optimize and everything, and then whatever adjustments you get from the data, you make to make things work. Okay, I will stop here. I think it's time, but let me know if there are any quick questions. Okay, thank you.
Yeah, there are no questions. Let's thank the professor. Thank you for accepting. Thank you for accepting to talk here. There are refreshments arranged at Coffee Hut. Please continue your discussions there.